Hey guys, welcome to lecture 8 of building a RISC-V processor. We're almost at the end of this course and this is going to be a very juicy lesson, so let's get into it. The agenda for today is to look at multipliers, pipeline stalls, and dividers, so adding a little bit of meat to our design. A multiplier is a combinatorial unit that takes two operands and produces a result. If the operands are excellent, the result is twice as big, and this is why we have lower and upper halves of the result in RISC-V instructions. The reality of a multiplier architecture is extremely complex. You have both encoded plus a tree multiplier. It can be a Wallace tree, it can be a Dada tree. For more advanced courses, link in the description, since these topics are all covered in my paid courses. For now, we will implement a simple one that respects all the real latency of a multiplier. So for example, this multiplier is going to be a 3 clock cycle latency. It's going to be fully pipelined, and we're going to see in a minute how the code looks like for this multiplier. So if we go and look at the code for the multiplier is fairly simple. We have the same output interface of the ALU with the data, the address, and the write enable. The tag for debugging. Here we have a first stage of flops where we actually flop the inputs. Here we perform a sign injection at the first stage, then we flop again. We execute the actual multiplication, we flop the result, and we go at the output. Now, one signal that we didn't have with the ALU is this busy signal. Why we need a busy signal? Let's go back to the slides. So even with this simple multiplier, we need to stall the pipeline. And suppose this sequence of instructions where we don't have any dependency between the two, but still we have the multiplier that takes 3 clock cycle to execute because we had three stages of pipeline, 3 stages of flops inside the unit, and the add that only takes 1 clock cycle. And we need to stall the pipeline of the second instruction until the first one is finished, otherwise we execute and commit out of order. And there's nothing bad with executing out of order. One of my advanced courses is all about executing out of order, but commit should always be in order. Otherwise we may break the flow of the program. So how does a pipeline stall look like? So we are asserting the busy signal whenever we have a valid multiply operation in the stage 1 and stage 2 of this multiplier. We'll see why we don't care about stage 3. So here's what's going to happen. This multiply busy gets propagated here up to the AXU module where the multiply is instantiated, and this multiply busy then goes to the core and goes down to IDU 1, where you can see here it appears as an input, and here is where it lands. And this is the stall logic that we're gonna dissect in a second. But here is where it lands. It lives in IDU 1, it gets used in IDU 1. So let's see when we need to stall. So we consider this sequence of instruction and we realize that in this case we need to stall. Are there any cases where we don't need to stall for the multiply? Well, let's take this sequence of instructions. So here, for example, we have a first multiply, a second multiply. Those two are not related. So here we don't want to stall since the unit is fully pipelined and we can send the two instructions in and they get executed in order and they get committed in order. Let's consider this other sequence of instructions where the first multiply feeds the second one. Here, there's a true dependency between the two instructions and we need to stall the second instruction until the first one is finished. Otherwise, we will have a read after write, a data hazard. So, a brief recap of when we need to stall for the multiplier is when the first instruction is a multiply and the second one is not, and when the first instruction is a multiply and the second one is a multiply, and there's a read after write dependency. And this is what we coded here. So we added a small flop to get whatever instruction we sent in, whatever instruction is currently being executed by the EXU stage. And if the last issued instruction is a multiply and the one that we're currently decoding is not a multiply and it's a legal operation and it's not a NOP, because we don't want to stall on NOPs, stall the pipeline until the EXU multiply is busy. Otherwise, if it's a multiply, the one that we're executing, and the one that we are decoding, it's a multiply, and there's a true dependency between the two, and it's legal and it's not a NOP, go ahead and stall whenever the multiply is still busy. We will get to the divide in a minute. So these are the two cases where we want to stall the pipeline when we send in a multiply. Otherwise, if we don't carve out this particular option for the multiply, we will not leverage the fact that the multiply unit is fully pipelined. So I've created two test cases here for the multiply. One is an extremely basic multiply that tests the actual multiplication unit, and we can look at the code of that test here. It's called basic mul. It's fairly easy. We are testing all the different kind of multiply. But then I've created a more nastier one where we have a multiply and accumulate. Again, if you do my AI accelerator design course, you're definitely gonna see a lot of this multiply and accumulate, where we have a true dependency between the two instructions, and then we have a bunch of random instruction after that to make sure that we are stalling correctly. So if we run this test, let's take a look at what we have in the output. So if we go on the RTL log for the last operation, so these are all the load immediate operations, and here you can see that we have the first multiply, then the second add that gets scheduled right after the end of the multiply. You can see we don't waste any clock cycle between the end of the multiply and the issuing of the actual add operation. I added a new column here where this is the cycle count of the processor. So here we execute a cycles 5, 6, 7, 8, 9. So it gives you an idea of how many clock cycles have passed between two instructions. So you can see that here we schedule immediately. So we are executing the most efficiently as possible. And the beauty of how we wrote everything is that if there's any forwarding that can happen, it will happen, because this logic is completely decoupled of this logic, and I made sure to deassert the busy signal from the multiply right when this logic kicks in. So this is why in the multiply we don't have the E3 stage here, because we don't need it. If we stop at E2, we make sure that the forwarding logic at the last stage of the forwarding logic is working probably and is kicking in as soon as we finish this multiply. So pretty cool stuff. We can see also on the multiply here that we are fully pipelining the multiply operations, even if we have back-to-back operation. So you can see these are all multiplies, and we are skipping the stalls because we don't need to stall. Because yes, the multiply unit is busy, but we know it's fully pipelined, and we know there's not a true dependency between those instructions, so we can just send them in, and we know that the multiply will honor those requests. So this is pretty much everything there's to know about this multiply and when we should stall the pipeline for the multiplies. Now, the divider is, in principle, is extremely simple as algorithm. We take one bit of quotient per clock cycle, but the problem is that it's one of the slowest units you can find in a processor. The algorithm that we're gonna use is an iterative non-restoring algorithm. So it means we calculate one quotient bit per clock cycle. It's a state machine. It's a non-deterministic latency, and in worst case takes 32 cycles. It's not pipeline. A unit like this, we typically call it a blocking unit in industry, because we're going to see that we need to stall the pipeline no matter what. Okay, so it's not like the multiplier that if I send something in the next clock cycle, if I don't have any dependency, I can send something else in. Here, if I'm dividing two numbers, I cannot send anything else in until I'm done. Okay, so this is why I've added a series of short circuit to like free the unit for very naive cases, like divide by 0, divide by 1, and for small numbers, we're going to use a lookup table. Okay, and all those short circuit close in one clock cycle instead of like potentially 32. Okay, let's take a look at the actual divide. So this is the divide unit, and I'm not gonna get too much into it because it's not the purpose of this course on digital arithmetic. This is something that if you want to dive deep into this stuff, you can buy one of my paid courses where I will analyze either one or another variant of these dividers. But basically what we have is the same interface that we have for all other units, and this is pretty much it. We have a input bank of flops to all the values of the inputs because they need to be kept there throughout the entire division algorithm. Here is where the magic happens. For the small numbers, this is a lookup table that I've created with Espresso, and here is where we implement the recursion algorithm, where we calculate one bit of quotient per clock cycle. Okay, and again, this unit works both for the divide and the remainder operation. So you're either outputting the quotient or the remainder. You are calculating both of them. So this is why here you have either A, which is the remainder, or Q, which is the quotient that you calculated. So this is how the divider works. And also the divider has an actual busy div stall signal that gets propagated to the EXU, and it lands on IDU1, and no matter what happens here, since this is a blocking unit, we need to stall the pipeline. So pipe stall comes high every time we send in a divide or remainder instruction. So how this pipe stall signal is used throughout the design. So let's start at the beginning, okay? And the beginning means the program counter. So here I've added a stall input control signal, and what this stall signal does, you see whenever here we have a stall, it doesn't matter if we have a load or an increment. So this is why we have the don't cares here. Every time we have a stall, we don't update the program counter, we don't increment it, and it's not a valid program counter to send out to the instruction memory. We completely froze the program counter. Okay. Once we froze the program counter, it means we're not fetching any more instructions. The instructions that we currently have in the pipeline needs to stay there, needs to be frozen. Okay, so this is why I changed all the flops before the EXU stage with enabled flops. And those flops are enabled whenever we don't have a pipe stall. And I did the same thing here in IFU, same thing in IDU 0, here you can see, same thing in IDU 1, but not in EXU, because of course in EXU we need to be able to continue executing. We don't want to stall the EXU, otherwise we lock up the entire design. So this is pretty much what is going on here, and this is how we are going to manage the pipelines. So if we want to take a look at the actual pipeline architecture, this is what now it looks like, and it's way more complicated than last lecture, but basically what we added is the 3 stages multiply, the divider, and now those multiplies and divider have busy signals that go into the stall logic of IDU1, and this stall logic fans out and propagates throughout our design to stall the program counter and all the flops between the EXU and the IFU. So basically we are freezing the upper side of the pipeline until the execution completes and we resume the execution. So this is pretty much everything that there's to know about multipliers, dividers, how we stall the pipeline to handle them. And if you want to learn more about dividers like SRT dividers, base 2, base 4, base 8, base 16, Newton-Raphson divider for AI, Goldschmidt divider. If you want to know more, check out the courses in the link in the description. I have basically all of them in one of my courses. So that's a wrap on today's lecture, and we are very close to completing this course. A couple of things that are left is how we handle branches. So how do we jump around in our program, and how do we access the data memory? So both reads and writes, we're going to see that a seemingly simple action like accessing the memory in read and write, it's going to create a lot of issues. We need to have a lot of logic to implement correctly the actual memory access, especially if we want a lot of performance out of this thing. So I'll see you in the next lecture, guys.